This is bubble sort, a simple way to sort a list by repeatedly swapping adjacent elements. To start with, we'll compare the first two adjacent elements and swap them if they are out of order. Then we compare the next pair of numbers and swap them if they are also out of order. We will repeat this process for all pairs in the list as we progressively move up the list. Now, by the end of this first pass, the largest number will bubble up to the end of the list. We repeat this process again, however this time we will ignore that final element in the list, since it is already in its correct position. Again, if two elements are out of order, we swap them. Once we complete this pass, the second largest element will bubble up to its correct position. We repeat this process, and with each successive pass of the list, we consider one less element that has already been placed in its correct position. On the final pass, we only need to compare the first and second elements in the list, and then we are done. Now, to think about how we can write a program for this sorting algorithm, let's first consider a general list of size n. The indexes of the list will range from 0 to n-1 if we use a programming language with zero-based indexing such as C. To keep track of our index into the list, we will use a variable j. Initially, j starts at index 0 and will successfully move up the list as we make comparisons and swaps between adjacent elements where need be. On the final comparison, j will be at index n-2, and the element at index n-1 will be in its correct position. So we can say that this first pass, j goes from 0 through to all values strictly less than n-1. Writing this out in a C program, we have this basic for loop. Okay, so we'll write our for loop and we'll initialize an integer j to 0, that will be our index, and we'll let it run through all values less than n-1. And then we'll check if the element at the current index is larger than the next element. We should then swap those two elements, and to swap them, we'll just use a temporary variable called temp. On the next pass, we continue making comparisons and swaps between adjacent elements. However, this time we'll stop when j is at index n-3, since the final element is already in its correct position. After making all the necessary swaps for this pass, the element at index n-2 will also be in its correct place. So for this pass, j goes from 0 through to all values strictly less than n-2. We will write n-2 as n-1 minus 1, and it will soon become clear why. So for this pass, let us now write our next for loop in our program. Okay, so this loop will be pretty much identical to the previous one, however, we'll just change the for loop condition. So I'll copy and paste the previous for loop, and what I'll do is, instead of having j less than n-1, I'll have it less than n-1 minus 1. We repeat this process on the next pass, and in doing so, we get the element at index n-3 in the correct position. For this pass, j took on values from 0 up to and not including n-3. Once again, we rewrite n-3 in terms of n-1, so we have n-1 minus 2 in our inequality. Again, let us write our for loop for this pass in our program. Once again, we'll just copy and paste our previous for loop, and all we'll do is change the condition so that j is strictly less than n-1 minus 2. Repeatedly applying this process, we continue to put elements in their correct place until we get down to the first two elements. For this final pass, j will only take on the value of 1. If we write this out as an inequality, we get j is larger than or equal to 0 and less than 1. However, let us rewrite this in terms of n-1 as we did for all the previous inequalities. So what we need to do is subtract some value c from n-1 to get it to be equal to 1. Solving this equation, we can easily get c equals n-2, and so our inequality will look something like this. Now we can go back to our program and write our final for loop. Once again, we'll copy and paste our previous for loop, and all we'll do is we'll change the condition such that j is less than n minus 1 minus n minus 2. What we should notice is that all of these for loops are identical except what is being subtracted from n minus 1 in the condition. In the first loop we subtracted 0, in the second loop we subtracted 1, in the third loop we subtracted 2, and we kept on doing this until we finally subtracted n minus 2. So we could combine all these loops into a single for loop where a counter variable goes from 0 through to n minus 2. Writing this out, we have I start off at 0 and go through all values less than n minus 1. Now we can use the variable I to subtract from n minus 1 inside the inner for loop's condition. As one final improvement, we can create a flag called swapped. If a swap was made, we set it to 1, otherwise we set it to 0. After every pass, we should check if we have made a swap. If not, then it means everything is already sorted and we can break out of our for loop without any extra work being done. To find the worst case time complexity of this algorithm, we count the maximum number of times the inner for loop runs. On the first pass, it runs n minus 1 times. On the second pass, it runs n minus 2 times. On the third pass, it runs n minus 3 times. And it keeps on decreasing until it runs once on the final pass. To sum these values, we can use Gauss's summation formula, and by plugging in n minus 1 into the equation, we find that it runs n squared minus n divided by 2 times. Ignoring lower order terms and constants, we can easily find that the worst case time complexity is O of n squared.